Okay, so continuing along the way, and I know some of these are rushed, but I've done a lot of graphing, especially my graphing video, that explains, the steps to do. You just follow the steps over and over again. So we're going to look at this one and ask yourself the nature of it. The nature of it is that I have an x squared here with 1 in front of it, and an x here. And when the power's 1 up, you have to divide this long division into this to find the oblique asymptote. There's no horizontal asymptote here. There is one vertical asymptote when x is equal to 1. And you should also find that this crosses the x-axis. So you're not going to be able to factor that really well. I think it's minus... you're going to have to take the quadratic formula calculator. And when you put in those values of 1, minus 3, and 6, you discover that there's only imaginary results, which means that this will not cross the x-axis. That's essentially setting this whole formula to 0, and this disappears, and when I factor that, I discover there's only imaginary solutions. In other words, it's a square root of a negative. In other words, it will not cross the x-axis. So you really only have to focus on the horizontal and the vertical asymptote. Now, since there's one vertical asymptote, when x is equal to 1, which is roughly here, that means it's probably going to do something like this and like this. But because it has a horizontal asymptote, it most likely could cross that horizontal asymptote, and thus it'll have a and then it'll go back to hugging it. So it's going to hug this vertical asymptote and then hug this diagonal asymptote, but often it crosses and then hugs it, which means we could be dealing with a max and a min. So that means the derivative of this is going to be important. The other issue here is it might cross the asymptote. Even if it doesn't cross the asymptote, we're going to be dealing with a max and a min. So that it's very important to find that horizontal asymptote and the formula of it. So what you do is you do long division of your, essentially dividing. That's what a fraction is. Right? It's taking this and it's dividing it by that. So what do I have to multiply x by to get x squared? X. And when I do, I multiply it here, I get x squared. And when I multiply it by the minus 1, I get minus x. And then just like long division, you subtract this bottom. Well, this becomes a minus and this becomes a plus. So that means x squared minus x squared disappears, but minus 3x plus x becomes minus 2x. Now we bring down the number. And we only need the next line. You don't need the remainder. How do I get minus 2x to become minus 2x? I multiply by minus 2. Now stop. That's the line formula of the diagonal asymptote. So now we have diagonal asymptote is simply a line that's been transitioned 2 downwards. Great. My only question now is, does my formula ever cross, does it ever equal, in other words, my diagonal asymptote? Keep a copy of that up here. And the first thing I have to do is multiply both sides by x minus 1 over 1 so that they cancel out here. And when I do that, I get x squared minus 3x plus 2. So I'm left with this. Then I have to subtract everything to the other side. And I see that that'll disappear, and that'll disappear. And this will just become a 4, and I'm left with 4 is equal to 0. Which means when you have a situation where it says something like that, it means it does not cross the asymptote. It's kind of like having negative square root for the quadratic function. It means it does not exist. Well, this means it does not exist. But I'm still going to be dealing probably with a max and min. So this is why the derivatives are important. Whoops. Keep the knowledge that it does not cross. You should always write down somewhere, does not cross, and show your proof. Okay, now you've got to take the derivative of this. So I'm going to go to a new page for the derivative because it takes up a lot of room. And as you've seen from my past videos, I tend to make mistakes on quotient derivatives, and that's because I rush. So you need to find the derivative of both these. The first one's derivative is 2x minus 3, and the second derivative is just 1, which will make it easy on us. So the whole point is we need to find the first derivative is equal to 0, and interestingly enough, this bottom part won't matter, but we'll put it in anyway, so we've got to square that. And then we've got to take the bottom function and multiply it by the derivative of the second function, which is just 1. Oh, no, it's not. It's this here. So that's a good example of me making a mistake. So we've got to multiply by 2x minus 3. Let's do that now. We get 2x squared minus 3x minus 2x, so minus 5x, and then plus 3. Okay, leave that alone for now. That's what we get. If I'm making a mistake, it's somewhere there. Then we have to subtract, and here's why I add a whole bunch of brackets, a square bracket and a round bracket. The second function, which is this, multiplied by 1. So fortunately it's this. However, this minus applies to every term in it. So we're left with minus x squared, and we're also left with a minus 6, which I'll try to squeeze in there. Okay. And the only thing that happens is this becomes a positive. Well, 2x squared minus x squared becomes an x squared. Minus 5x plus 3x becomes a minus 2x. Plus 3 minus 6 becomes a minus 3. That's what we have at the top. If I factor that, I discover I'm dealing with minus 3 plus 2. If I factor it, they have clean factors. Plus 2, sorry, minus 3 plus 1. That's what I'm dealing with. Those are the factors. It will not cancel out with anything down below, so that's good. So I'm left with this. This is the first derivative. Now, you make it equal to 0 to figure out the max and the mins. This goes up and disappears. So this is equal to 0, which means that I'm going to have a max when x is equal to 3, or min, and I'm going to have a min when x is equal to minus 1. And it's going to tell me a lot. So now I have to go back to the original equation, and I have to plug in minus 1 into this. So I get 1 plus 3, so 4, plus 6, so 10, divided by minus 1 minus 1 minus 2. I get minus 5. So that means one of my max or mins will occur at minus 1 comma minus 5. Now I plug in 3 into it, into the formula, the original formula, not the derivative. And I get 9 minus 9, that's convenient, plus 6. So I get 6 divided by minus 3 minus 1 divided by 2, 3. So that means my other derivative is located at 3 comma 3. Sorry, my other max or my min. Fantastic. Now you should also have kept, I'm just going to make a copy of those, you should also have kept your first derivative around, because you're going to have to take a second derivative. Normally you'd take a second derivative to see if that's a max or min. However, due to the nature of this graph that I've already determined, I discover, and here's the asymptote. The asymptote's at x is equal to 1, right? X is equal to 1. I discover that one of my things will be at -1, -5, which is right over here. And the other one will be at, let me just get rid of this other drawing. Will be at 3, 3, which we'll determine is somewhere over here. Since I know that it must hug the asymptote and it must go through that point, I know this whole graph over here is going to be on the positive. I really don't have to take a second derivative, and my 3 point will be a minimum. I know that just from the nature of this graph, which means this other one, which must hug the asymptote, will go through -1, -5 over here, will be its max. And you might say, well, how do you know it doesn't go here and down here? And that's because this point I know is below the vertical asymptote, just as this point is above. However, for argument's sake, we will take the second derivative. And for the second derivative, it helps if you expand the top again. So you get x squared minus 2x minus 3. And you use that to find your second derivative. It also helps if you know what the bottom's going to expand to. It's going to expand to x squared minus 2x plus 1. Because taking the derivatives of these two things is easier than applying the chain rule. Now, I will keep the first derivative around somewhere, and I'll note that it's the first derivative, just in case. And now I'm going to find the second derivative. And I don't really need the first formula anymore. I just need to figure out what's the derivative of that. Well, this is the numerator derivative, and this is the denominator derivative, and I need to find the derivatives of those. So I take a derivative. You're essentially taking the derivative of the derivative. So this is the derivative of the top one, and this is the derivative of the denominator, which means you must take your denominator and multiply it by your derivative of your numerator. You can see how complicated it is, but here's the good news, and I'm going to put it in good news terms in a second. And you must take your numerator, you subtract, and you must take your numerator and multiply it by the derivative of your denominator, which you've discovered is this. Do they both have the... Oh, they both have the same derivative, so it doesn't really matter. Okay, now the good news is you do not need to expand that. And now you also have to square, again, this whole thing will be squared. The good news is you've already figured out that -1 and 3 are the x values for your min and your max. You can just plug this in here. So I get 1 plus 2, so 3 plus 1, 4. And I must multiply it by -2 minus 2. I must multiply it by -4. So this whole left side becomes -16. -1 over here becomes 1, plus 2, so 3, minus 3, 0. Make sure that 1, plus 2, so 3, minus 3, 0, and it's going to multiply this, so this whole right side is going to become 0, so you don't have to worry about that. So you're only dealing with -16. When you put the -1 into the bottom, you get 1, plus 2, 3, plus 1, 4, squared. 16. So it's -16 over 16. That becomes a -1. So now, and actually you could only just need to determine if it's a minus plus. So now this -1, which was -1 comma -5, I know is negative in the double derivative, tells me it is indeed a, well actually that tells me it's a maximum. That's right. Negative tells me it's a maximum. If you take the 3 now and do the whole process again with the 3, 3 squared is 9, minus 6 is 3, plus 1 is 4, times 6 minus 2, 4, so you're dealing with 16. Over here I get 9, minus 6 minus 3, so it becomes 0 again, so you're dealing with positive 16. And now I'm going to discover it's going to come out to 16 of the positive 16 over positive 16 is 9, minus 6, plus 3 is 4, squared is 16. 16 over 16 becomes positive. It doesn't matter if it's positive 1. That positive tells me that 3 comma 3 spot is going to be a minimum. That's what double derivatives are positive. So you can see that if you couldn't graph it, you will, from the double derivative, determine that this one has a minimum and this one has a maximum. Let's go ahead and put this into Desmos. Oh, you could also find where the y-intercept is if it existed, and I believe it will exist. That's when x is 0, so you get 0 minus 0 plus 6, and 0 minus 1 minus 1 minus 6. So at 0 minus 6, which is on this side, obviously, because it's got to hug this asymptote, it's going to go through the y-intercept. So that's a good point to have too, 0 comma minus 6. So let's put this into Desmos. So you're going to get x squared minus 3x plus 6. I forget what the middle term is already. X minus 1. And according to me, I know a couple points. I know that it's going to go through 0 comma minus 6. I know it's going to go through 3 comma 3. And that's going to be a min. I know it goes through minus 1 comma minus 5. And that's going to be a min. What other points did I collect? Oh, here's the horizontal asymptote. And here's the vertical asymptote. I'm going to make both of them red. And now let's see if we got it right. Let me make sure I got it right here. X squared minus 3. I have plus 6. I knew there was something wrong. And now let's turn it on. Boom. Got it. And I'll just make it blue. So all those points we were able to get, and there's that y-intercept, and it allows us to graph it. Now, obviously, if you study your graphs more, you'll get a good idea of what happens in these graphs. So it's a really good idea to study your parent graphs and even adventurous ones. You know what square root of x does, but what does a cube root of x do? Well, that's good to know. What about a fifth root? Same thing, seventh root. So those are all good. What about a quarter root? Yeah, a quarter root behaves like a square root. So it's good to know that when it's an even number, it's going to behave like a square root, and when it's an odd number, it's going to produce something you've never seen before. It's also good to know, let's say you have a parabola that's slightly below. What happens to that parabola when I absolute value it? Well, all these negative y values are going to come positive, so you're going to get a weird shape like this. Like that. And really, it makes sense. When you think about it. All those red line is simply the bottom blue line being made positive. So the more you understand these things, the better. You should also know what happens when the bottom is always going to be positive. So let's say I have x cubed at the top, and I'm going to divide it by x squared plus 1. You should notice that that's never going to create a vertical asymptote because the denominator can never be negative. It can, however, when you subtract 1, because there's an area when x is 1 or x is minus 1 where the denominator becomes 0, but not when you add 1. So all these things you should learn just roughly so that you know what to expect. Let's look at this one. This is exactly what I was talking about. This is a cube root. And the cube root, even though it's squared as well, Essentially, you're taking the cube root of inside and then squaring it. As we learn, the cube root produces something like that. And that's because if you look at it in writing, so a cube root, I can have a negative result. But then I'm going to, but then I'm going to square it. So anything in here, no matter what I do, is going to be positive. Because when I square it here, it's all going to be positive, which means I'm going to have something that never reaches 0. There will be a possibility, of reaching 0, because if x is 4 in here, I get 0, cube root is 0, squared is 0, which means it's going to touch 0, 0. But that's the lowest it's going to get. What happens, and this is always a good thing to measure, when this is positive infinity? Well, I get positive infinity cubed root, and then squared, it's going to be positive infinity. So that means it's going to go something like that. What about when I take negative infinity? Negative infinity, when I cube root it, is going to be negative, but then when I square it, it's going to be positive. So it's going to go like that. So since it goes through 0, 0, we're going to have a graph that whatever happens on this side will be perfectly mirrored on this side, because it's symmetrical through 0, 0. Now that's just a guess. The other thing that's possible is it might go up and then go down. So you might have a max. Well, it might go down a bit and then go up. So you might have a weird wiggle here. It might go up a little, come down, and then go up. You have to examine it a bit more, and that's where the first and second derivative come in. Since we know roughly where it's going to exist, what happens when x is 0? When x is 0, you get minus 4 squared, 16, and then cube root. So there's not really a good, you could do 8 times 2, and the cube root of 8 is 2. So you're going to get 2 times the square root of 2, which means it's going to cut through. Oh, and that's also interesting. This will not be symmetrical through 0, 0, because the number that creates that symmetry is when x is 4. So it's going to be like 4, 0. So it's going to be symmetrical around that point. But it's interesting to note that 4, 0 is an x-intercept. When I make x 0, I get minus 4 squared 16. Cube root of that is 2 times square root of 2. If I put that in the calculator, just to get a rough idea of what it is, I'm going to get 2.82, which means it's going to pass through the y-axis at 0, 2.82, which is really accurately this number. This is actually what you would put in brackets if you wanted to be very precise, because this is more precise than that. Okay, so you got a lot of information already. You would technically find out what happens immediately to the left and the right of 4 to make sure it's positive, but I already know that 5 minus 4, which is to the right, is 1 squared. Cube root is 1. So I also now have 5, 1. Then it's going to go down to 4, 0. And I'm going to suspect that there's going to be 3, 1 as well. 3 minus 4 is minus 1. Squared is 1. Cube root is 1. Sure enough, 3 comes. So there you got 2 valuable numbers. And it's going to go up. So the only question is, does this have a max or min? So let's jump right over here and put in what we know. And we're just going to leave the other stuff blank. And we know that we're going to have a point 4, 0. We know we're going to have a point 1, 5. We know we're going to have a point 3, 5 as well. Not 1, 5, 5, 5. And 3, 5. And we might as well label them. We also know we're going to have a point 0, 2 times the square root of 2. Right there. Now notice already, and I should have noticed, that 2.2 is smaller than 3. So we are indeed dealing with, and we could have deduced that just from our numbers right here, when we saw that 2.820 is the y-intercept, and that 3, 5, the 5 is higher. So now I know that it's going to go through the x-axis, it's going to come up here, and it's going to kind of dive and then probably go up. So we're going to have a min. and it's going to do the same thing on the other side perfectly. We're going to have a max. And interestingly, the x value here for this min is going to be the same distance from 4 as the min value over here. And they're probably both going to be mins. So again, the derivative is important. Let's use the chain rule for the derivative. 2/3 times x minus 4. And what's 2/3 minus 1? Minus 1/3. What does that mean? Now, and what's the derivative of the content? The derivative of the content is just 1, so we don't have to do anything. What does that mean? That means we actually have 2 on the numerator, 3 on the denominator, and also in the denominator we have x minus 4, and it's going to be cube rooted. Cube rooted. That's what the negative third means. So this is the first derivative. Interesting that that's interesting to me, because that's going to indicate that there is no 16 cube root, that there is no maximum. Oh, you know what? That's the mistake I made. It's not 3 comma 5 and 4 comma 5. It's 5 comma 1. So there is no max. My bad. Now, how do I know this? Because this is the first derivative. When I set it to equal, this whole thing gets multiplied to this side and disappears, and I get 2 is equal to 0, which is an indication that there's no max or min, because the derivative can never equal 0. So right away, I could see that I made an error in my little graphing, and it's really because I transposed the buttons wrong. So that means if I take a picture of this, by the way, this is 4 away. You're also going to have a spot over here at 8, comma 2.8. That's my prediction, and you can figure out how I knew that. 8 comma 2 times the square root of 2. I'm going to tell you that we're going to have same dot here as this, because this is 4 away from the bottom, and then 4 away we're going to have that. So that means if I'm going to graph this without the information, here's the axis. Right here, I'm going to have a dot right there, dot 4 0. I'm going to have 5 1, 4 1, and right over here 0, 2.8. So I'm going to have a graph like this. And it's probably curving. Let's see how it's curving. I think it starts with a little curvy here, but then just keeps going. Okay, let's turn it on. So we get f of x is equal to x minus 4 to the power of 2/3. Oh, it's okay. It does have a little curve. Oh, and I must have done a mistake here on the, let's do square root of 16 instead. Oh, no, cube root. Yeah, that's the mistake I made. It's not square root. It's times 2 to the third, the cube root, times 2 to the third. I could have also left it in its original form, which is 16 to the power of a third. Those are the actual points, so small calculation error, because I forgot it was the cube root of 2, not the square root. And you can see we perfectly predicted all the points. There's also only one point it touches the x-axis at 4. There you go. So it helps to know a lot about your graphs before you do it. Yeah, we did number 5. This is kind of stupid, but we'll try it. So they're just giving you missing values again. A, B, C, D, so that the curve defined here has a local max point at 2, 4. So that means the second derivative is going to be negative, and the first derivative is going to be equal to 0. Let's start by taking the first derivative. 3ax squared plus 2bx plus c is equal to our first derivative. There. That's our first derivative. We also know it goes through the point 2, 4. The graph goes through 2, 4. So that means when y is 4, what's 2 cubed? 8. What's 2 squared? 4. What's 2? Just 2. And we don't know D. We know it's a cubic, right? The graph is a cubic. We know they've given us a max point. It could have a min point. And it also, here's an important piece of information, a point of inflection at origin. So that means at 0, 0, the second derivative, so we need to find the second derivative, 6ax plus 2b is equal to the second derivative. And that means x is going to be 0. This whole thing is going to be equal to 0 when x is equal to 0. That's what a point of inflection is. The double derivative is equal to 0. And we happen to know the x value when that happens is at origin, which is 0, 0. So that means the x is going to be 0, so this will disappear. So we're left with, for that, 2b is indeed equal to 0, which means b is equal to 0. So right there we have a value. B is equal to 0. We got that from the second derivative. And that helps, right? So if we put it up here, and they want us to sketch the curve after, we know that this middle term is going to disappear. Okay, we also know that at the 2, 4, this equation is going to be 0. So that means when x is 2, 3ax squared becomes 12a. And when x is 2, plus 4b, but we've determined b is 0, so let's get rid of it. And the only thing we're left with is c. And we know that's going to be equal to 0, which means that c is equal to minus 12a. And finally, we're left with this formula here. But we've discovered that b is 0, and we've discovered that c is minus 12a. What's 2 times minus 12a? Minus 24a. So that whole thing becomes 4 is equal to minus 16a plus d. Not super useful, except now we know that d is equal to 4 plus 16a. The only problem is we haven't really come up with a good way of figuring out the missing points, except that we know it goes through origin, right? That was another hint they gave us. And it's easy to miss that. So far we have b is equal to 0, c is equal to minus 12a, d is equal to this, and the only thing we don't know really is a formula for a, right? So we're just going to keep these derivatives here. But we do know, going back to the main equation, that when x is 0, y is 0. 0. And when x is 0, this becomes 0 plus 0 plus 0 plus d, which means that d is equal to 0. So now we have two formulas, and we know the answer for this one is 0. So we can immediately figure out that 16a is equal to 4, minus 4. So a is equal to minus 4 over 16, which is minus 1/4. So we're left with a formula of y is equal to minus 1/4 x cubed. We've determined that x is 0, so 0. And we've determined c. What is c? c is minus 12 times a. So minus 12 times minus 1/4 becomes positive. 12 divided by 4 is 3. So we determine that c is equal to 3. If my calculations were right, even if they were wrong, this is the correct way to do it. And suddenly we have the last term, which is 3x. Now, before I go to the graphing, I want to make sure of a couple things. When x is 0, will y be 0? Yes. When x is 2, will y be 4? because that's important to see if you got the formula right. So 8. 8 times minus a quarter becomes minus 2, plus 3 times 2, 6, becomes 4. So indeed, we got that point so far and that point, which means all my values are correct, hopefully, here. The only thing you now check is to make sure that when I take the derivative, does the derivative match? But instead, I'm just going to graph this. I'm going to get rid of all these points here. And I'm going to do y is equal to negative a quarter. I know it's an x cubed. I'm going to turn off the graph to give you a rough idea of what the graph looks like before doing this. And then it's plus, what was it, plus 3x? Okay, what would that graph look like? What would that graph, assuming I got it right? Well, we're talking about a cubic that has a negative leading coefficient. So it's going to start up here. We know it goes through 0, 0. Okay? We know it goes through 0, 0. Now, whether it goes through or bounces off, we don't know. So we should look at our formula here, and we notice we can take a x out of it. When we take an x out of it, we get negative a quarter x squared plus 3. We're going to find our other x intercept, and that's when this part here is equal to 0. So negative a quarter x squared plus 3 is equal to 0. So when negative a quarter is equal to negative 3, when I multiply it by minus 4 over 1 times minus 4, I get x squared is equal to 12. Or x squared is equal to 12, which tells me that it's going to go through the x-intercept 2 other points at square root of 12, comma 0, and at negative square root of 12, comma 0. We also know it hits a max point at 2, comma 4. What roughly is negative square root of 12? It should be above 3, because square root of 9 is above 3. It's 3.46. So, since it hits a max at 2, comma 4, we also know it'll probably hit a min at minus 2, comma 4, because it's pretty symmetrical. So we're going to be dealing with a graph like that. And that's because the x-intercepts are an equidistance of the origin, which means the maximums will probably be mirrored as well. So I've got 2 extra points now that I'm quite sure. And sure enough, if I put minus 2 into the original formula, I should get that. So minus 2 cubed is minus 8, divided by minus a half is plus, minus a quarter is plus 2, plus 3 times negative 2, which is negative 6. So I get 2 minus 6, which is minus 4. So sure enough, I got that. Now, let's go and turn on our graph and hit home. And now I'm going to put 2, comma 4. And I'm also going to put negative 2, comma negative 4. Look at that. And it went through origin. And you can ask Desmos to take the derivative if you switch this to f of x. And you can go ahead and say when is f prime of x equal to 0. And it'll show you the 2 max mins. And then you can say when is f double prime x equal to 0, and it'll show you the origin as the only spot. There you go. Now cubics obviously are easy to graph compared to other graphs. Onwards. Almost choked on my coffee. Given the following results of the analysis of function, sketch a possible function. Oh God. I mean, I could. So they're telling us it goes through origin. There's a horizontal asymptote at y is equal to 2. There's a vertical asymptote at 3. And when, oh geez, there is going to be a negative slope No, the derivative is always less than 0, so it's a negative slope. The double derivative is less than 0 for when x is smaller than 3, so it slopes downwards. And it continues to slope downwards, and then slopes upwards for 3. Yikes. Pain in the butt. Like, work with your professor for those. I don't like doing those. Okay, number 8 is kind of silly as well. The reason I don't do those hypothetical ones is because I don't see a practical scientific purpose to it. However, if your teacher wants it, do what they did. Now, so any positive constant, that means it has to be 1 and up, plus 1 and up. So look at this theoretically. If it's 1 minus x up here over 1 plus x squared, or 2 minus x over 2 plus x squared, let's put it in the x squareds first. So we're talking with a minus x over x squared, which means we're talking about y is equal to 0 as the horizontal. And then over here it's plus a number. So this bottom is always going to be positive. And it's plus a number squared, whereas this is just plus a number. So this is going to get much bigger than the top. So we're looking at 0, we get minus x over x squared, which is simply minus 1 over x, when the constant is, when the constant's 0. No, when x is 0, we simply get constant over constant squared, which is simply 1 over the constant. So when x is 0, the y-intercept is going to be tiny, 1 over the constant, and will get tinier as the constant gets bigger. And as I said, however, when x is negative plus a constant, there will be, when we get in a negative infinity, the top becomes positive and the bottom stays positive. But when we get into positive infinity, the top becomes negative and the bottom becomes positive. So what I think you're going to see is a rise, and then it's going to hug, and a rise, and then a hug, and it's never going to get negative. So that means there's going to be a max, and two maxes most likely. Let's just plug this into Desmos as it is. And we're going to put a k value down there and divide it by x plus k squared. Oh, I got that totally wrong. Of course, there's going to be an asymptote. I forgot that there's a possible asymptote down below. But I'm going to change values of k, where k goes from 1 to 10 by steps of 1. And I'm just going to play it. Wow, I totally got... Oh, yeah, of course. Why did I think it was always positive? I already knew it was negative on the one side. So you can see I totally botched the analysis, and that's because I rushed through it without realizing there's a vertical asymptote and forgetting that there's negative values of infinity. Like there's negative y values when I cross the asymptote. And I already figured that out, so there's no way it would look like the other thing. But notice that the k essentially just makes it translate. Makes the asymptote translate and the whole graph translate as x goes up. You can also make this, go all the way up to 100 and hit play. Interesting that it only translates to the left. And that's because plus k squared here. Obviously, when x is equal to k squared, that's when the asymptote happens. So sorry about botching it, but really, that's really why I don't really care about the theoretical one. Sketch the curve defined by this. Oof. So you get a cube root of something multiplied by the square of a cube root. So this is always going to be positive, but this is always going to be negative. It'd be interesting to see if I expanded this and just left the cube root to see what would happen. If I just squared it. Okay, well, that's sort of an interesting one. I don't know if, again, it's worth doing it, but I'll keep both these around. Okay. So again, let's look at possible values of x. When x is 0 on this one, you get 0, and that's going to make the whole thing 0. So we're going to get a 0, 0. When x is positive, these are both positive. Also, wait a minute. When x is negative 3, this becomes 0. So over here, we're going to have another x-intercept, negative 3 comma 0, and 0 comma 0. So you found the two x-intercepts. Now, when this goes above negative 3, in other words, when it's on the right side of negative 3, this whole thing, well, no, this whole thing will stay positive no matter what. But when this thing goes to the left of 0, this whole thing becomes negative, which means we're dealing with something like that. When everything to the left of negative 3, this still stays positive, but this stays negative. Ah, interesting. So everything to the left of negative 3, so I get negative 3, I get negative 4 here, but it's squared, so it's positive. But over here, negative 4 stays negative, so the result will be negative, which means it does something like that. Let's make sure that, and it might be a cusp situation. It might be wanting to go here, and it just goes like that. I think we're dealing with a cusp twice. What happens when we're on, let's make sure that when I'm at minus 2, that's what happens. Minus 2 plus 3 is 1, so I get 1 squared cube rooted. Minus 3 cube root doesn't stay negative, so I get minus 3 cube root times that. So that area is definitely negative. Now let's look at what happens when I'm above 3. This will stay positive, and this will stay positive. Okay, so I've got some weird thing going on. Now, if I was just to take it as x cubed times x 2/3, I'd be allowed to add their fractions. 2/3 plus 1/3 is simply x. So I think what's going on is this line is normally a straight line. This line is normally be a straight line that's adjusted to the left by, like, well, hang on, right, it's normally like that. It's just normally y is equal to x. Except, right here, in the zone between minus 3 and 0, this graph is getting wonky. This graph is getting wonky. And even right up to there. I think it's going to curve up, touch, do this weird bounce thing, and touch. And a good example would be taking the value of minus 1.5 to see what the min point is here, if there's a min point, or taking the first derivative to see if there's a min point. Okay, so let's practice taking the first derivative. First derivative of the first term, oh, we have to use the product rule here. So the first derivative of the first term is 1/3 times x to the negative 2/3, which is simply this. Times this. So it simply becomes x plus 3 to the 2/3 over 3 times x to the 2/3. And then I have to add, and the derivative of this becomes 2/3, and it becomes x plus 3 to the 1/3 down here, because it becomes negative 1/3 up top, times this. The only way I can add them is cross multiply, and then set it equals to 0. So let's do that. When I cross multiply, I get 3x cubed times 3x 2/3, and that becomes 9, and they have the same base, 1/3 plus 2/3, x, 9x. So this becomes 9x. When I cross multiply the bottom, it's 3 times this object that has the same base as this object. It becomes plus 3, x plus 3, because the fractions cancel out. And the bottom of the numerator of this thing, so I get 9x plus 3 times x plus 3, and the bottom of it becomes those terms with those numbers. Actually, I might have gotten the 3's wrong, because there's 2 3's here. So I think there's another 3 I have to... Actually, you know what? Let's go back and do this properly. See what happens when you rush. But I had the right idea. What's the derivative of x minus 3? X minus 3's derivative is 1 over 3 times x to the 2/3. Like that. No, I think I got it right. What's the derivative of the second one? It's 2 over 3 times x plus 3 to the 3rd. Like that. The product rule says I must take the first term, x to the 3rd, and multiply it by the derivative of the second term. And then I must add it to the second term multiplied by the derivative of the first term. So I essentially get this. In order to add fractions with different denominators, I must cross multiply. Three times 2 to the x, and then 3 this times this. And the denominators will simply be the terms multiplied. You're going to discover that those denominators don't matter when we're looking for the derivative. 3 times 2, and these have the same base, 2/3 plus 1/3, you get 6x. Plus x plus 3. What happened to the other 3? Oh yeah, there we go. Has the same base as this one. So these, when they multiply, become x plus 3 to the power of 1 times 3. When I expand 3 times x plus 3, I get 3x plus 9. When I add it to the 6x on the left, I get 9x. Sorry, that should just be a 9 there. That should just be a 9. I get 9x plus 9. Now, when I set, this is my first derivative. When I set it to equal to 0, I get 9x plus 9 is equal to 0, or 9x is equal to minus 9, or x is equal to minus 1, which means I'm going to have a max or a min when x is equal to minus 1. Now, we go back to our equation. the cube root of minus 1 is minus 1. Minus 1 plus 2 is 2. 2 squared is 4. And the cube root is unknown. Now, I can find the cube root by putting it to the power of 1 divided by 3. I get 1.33. So, at roughly negative 1 and a third, at negative 1x, I get negative 1 and a third y. So that will be a min point, because we already determined that the graph is going to look like that. So at that min point is going to be minus 1 minus 1.33. I'm not going to take a second derivative. It would be insane. So let's throw this on Desmos. X to the power of a third times x plus 3 to the power of 2/3. And let's zoom in. And look at that. Oh, I got the y wrong. So let's find f of minus 1. So yeah, I had to find the cube. Oh, I forgot to square the 2. No, I got 4. So let's find out what this cube root of 4 is. There you go. I did the cube root incorrectly. So what I should have done in the calculator was take 4 and go to my second function and just actually use the cube root function, get the right number. So anyway, other than calculating the y value for that, it's pretty good. So minus 1 comma f of minus 1. Label it. I also got the curve here wrong, but I think I could have figured that out. But look, if you zoom out far enough, it looks like the line y is equal to x, doesn't it? And that's because if you ignore the 3, that's precisely what you would be left with. That's y is equal to x. It's just the bigger this number is, the more of that weird thing it's going to cause. More of that disruption. And we sort of figured it out. It's because it creates a negative bump. Next one, find the horizontal asymptotes. Horizontal. Okay. This is to the 1. And what is essentially x squared square rooted? It's x. Now, we should actually, that's really interesting. It doesn't have any vertical asymptotes. That's interesting stuff. And you might think this shouldn't either, but it's actually a square root, so it will. Those are damn good questions. Let's tackle this one first, just on a hunch. I'm going to multiply it by its conjugate. Which means the denominator is going to become this. And it's going to be the same graph. But when I multiply these out, I discover that this disappears, the middle term disappears, and then this becomes minus whatever's the content. So essentially I get t squared plus 4t minus t squared minus t. So you can see the t squareds cancel out, and I'm simply left with 3t at the top. That doesn't necessarily help me. The power is bigger up top. The power is bigger up here. So that I believe what it means is there's going to be a horizontal or diagonal asymptote. I don't believe there's going to be, because the power up here and the power up here is roughly the same. Those are damn good questions. This gave me a better idea of what's going on, though. 3t over this thing, which can only produce positive results. So I believe it's only going to be positive. Oh no, this can be negative on the top. So the 0, 0 is something weird going to go on. Those are really tough. Let's try... Just get rid of this for now. It's interesting. I would think it's y is equal to 1 for this one, just because they both have a 1 in front and they're essentially the same powers. And I believe it's going to cross y is equal to 1. You could take plus infinity. And the top's going to stay plus infinity, and the bottom is going to be squared infinity plus 1 squared infinity. So it's going to be slightly bigger than that. And then when you take the square root, it's going to be infinity, but slightly bigger. So that means this will be equal to 1, but slightly less than 1. So I believe as we hit positive infinity, if the horizontal asymptote is at 1, it's going to be just on the underside of it. I also can see that it's never going to be positive here. It's always going to be positive here, but it's going to be negative here. So it's probably going to do this. And then on the other side, it's probably going to try to approach negative 1. So in this case, you have to put your negative infinities in. Sure enough, the same thing happens, except I have a negative over here with a slightly bigger thing. So it's never going to reach the bottom asymptote, horizontal asymptote of -1. And it's also from realizing that this is always going to be positive and this is always going to be negative. So you kind of have to apply some logic here. So let's put it x divided by, and we'll use the same thing for the other one, x squared plus 1. Let's put y is equal to 1. Y is equal to -1. And sure enough, that's what we have. And if we zoom in, let's just take a value of f this, and you'll see it never quite reaches 1. And if I take a negative infinity number, it never quite reaches -1. Yeah, it does there because it rounds up, but it's really never reaching -1. Good, that was easier than it looked because we used positive and negative infinity. Let's see if we can do the same thing for the other one. The other one's a little trickier, and I kind of wish I'd kept my conjugate, because I can remember that it becomes 3t on the top, which is a lot easier to figure out. But let's have a look. This is a square root of a square again. So it's essentially going to be t plus some number. And other than 0, so when t is 0, we get 0 minus 0. So we do have an origin. Goes through origin. And when it's small, like when this is 1, this stays positive. When this is -1, though, this becomes 1 minus 4, and we get non-existence. So between t squared is equal to -4t. Divide t on both sides. T is equal to -4. So t cannot be between -4 and 0. I don't think we have an existence, because when this is -3, you get 9, -12. Only when we hit -4 do you go back to 0. So now there's another point, -4, 0, where this will be 0. But this will be a bigger number, and we're going to get minus. So anyway, let's just ignore that -4, 0. The point is, this can't exist between 0 and 4. So x cannot exist between 0 and 4 for this one. Between this one, t squared cannot equal -t, or must be bigger than -t here. In other words, t must be bigger than negative 1. Because when it's negative 0.5 here, oh no, this is fine because it's plus. So this will always be a positive number. We just have a problem between 0 and minus 4 on this graph. Now, when t is positive infinity here, we get positive infinity squared plus 4 times positive infinity. That doesn't matter so much. When we take the square root of it, we get infinity. When we get the same here, we have to subtract the square root of positive infinity, which becomes infinity, but it's only then that we see that we've got 4t, or the square root of 4t, minus the square root of 1t. We essentially get an infinity minus 4 times an infinity times minus 1 infinity, so we're still positive infinity. When we take negative infinity, we get infinity squared plus 4t. So that's positive. And over here, we get minus infinity squared plus 4t. We get the square root of 4t minus 1t. So we can see we're almost always we're actually gonna reach that. That one puzzles me. I kind of wish I'd kept the conjugate up. Let's try the conjugate again. I get t squared plus 4t minus t squared, so 0, plus minus t. Yeah, I get 3t up top, and then all this I get on the bottom except positive. So I believe 3 is the defining number. So I believe you're going to have a y is equal to 3 here. And I don't believe this bottom can ever become negative except between negative 4 and 0. There's some sort of no man's land going on. Let's find that out. Yeah, no, this can't exist. So you get no report when we're at minus 3 here. And it goes through 0, 0. Bizarre. I have no idea what this looks like. Well, there's an example sort of giving up. When I'm left here in infinity, I get 3 times infinity. And this is positive. Wow. So now I get 2 infinities. Wow. Plus the square root of 5 infinities. I really can't see what it's going to become. I think I'm dealing with like 3 over square root of 5, whatever that is. Let's have a look at what this graph looks like. T squared plus 4t. And I probably should have used limit. Let's use x. So yeah, there's that no man's land that can't exist. T squared plus t. It would help almost to know what that graph looks like. Just going to put it down here and turn this off. So that has a no man's land as well, between 0 and 1. And when I subtract them, let's see y is equal to 3. Let's see y is equal to 3 by the square root of 5. Yeah, it was that. Y is equal to negative 3 over the square root of 5. No, it wasn't that on the bottom, though. Oh, yeah, it was. They're both trying to approach that. Not quite accurate, though. I think I had to use the technique of dividing it out. There's a good technique in the book where it divides these things out to see what's left. For instance, if you put that all over a fraction, you get a better idea. Anyway, very hard to see what it becomes. However, there is that no man's land that we correctly predicted. I think I had to see what it becomes at negative infinity more accurately. Yeah, because the top becomes, as I learned here, the top becomes negative, and this stays positive. So yeah, I could have figured it out using the conjugate version. Sorry for wasting your time, but that's the kind of things you have to do. Show that for any cubic formula. Well, there's always only one point of inflection for a cubic. We've already figured that out. Cubics only have one point of inflection. It's impossible for a cubic to have any other points of inflection because they only turn around once. When you look at a cubic, this curve is following the normal process, normal process, normal process, normal process until it hits here. That's the point of inflection. Then it changes directions, but after that, it can never changes directions again. That's the nature of a cubic. A cubic will have one point of inflection. A quartic can have up to 2. 5 penta will have up to 3. So it's essentially the term minus 2 is how many points of inflections you can have. And how can you determine that point of inflection? When the double derivative of this is equal to 0. So the first derivative is that. Plus 2bx plus c. That's the first derivative. The second derivative is 6ax plus 2b. And when you set that to 0, you get 6ax and the slope of the curve at that point. Oh yeah, so first I have to figure out what value of x I have. So that's the value of x at that point. To figure out the slope at that point, I have to take the first derivative and put that in. So I get 3ax squared plus 2bx plus c. And at that point, that's the first derivative. That will give me the slope if I plunge in my x value. So I get 3 times a, and what's my x value? Minus b over 3a. So clearly the 3a's will cancel. And then plus 2 times b times minus b over 3a. So you get minus b squared minus 2b squared over 3a. So the only thing I'm worried about is 3 times a times minus b. So where did the minus b come from? How come there's no minus b? I'm close. Okay, again, I've determined that x is equal to this, and I'm just going to make sure. Oh, it's squared. Sorry. Oh, no, yeah, it's squared. So it's 3 times a times minus b over 3a squared, which becomes b squared over 3a squared. These cancel out, so it just becomes 3b over 3a plus, oh, I had to keep that, sorry. And this is the x value when at the point of inflection, and I have to put it in here and make it equal to 0 to figure out what the equation is, or what the slope will be. Since you won't have a number, you just plug it in. Plus 2b times my minus 1b over 3a. This one's not squared. This is squared, I forgot. Which I get minus plus minus, so that becomes minus 2b squared over 3a. Over 3a plus c. I can add these because they're like terms. B squared minus 2b squared is minus b squared over 3a. And if I rearrange it, this is what I get, which is their answer. So that's the slope. And how I did it was figuring out the second derivative, setting that to 0, figuring out what x is equal to in that situation. Then I know the first derivative gives me my y value at that point, and that's because, will give me that slope at that point. So I plug that in where I see x and solve it as far as I can, which is that. And that is the slope of the derivative, that is the slope, which is what the first derivative is, the slope at that point. That's it. Sorry I botched a few there.